I'd like to welcome you to our second session on architectures. The first speaker will be Chella. Antonio? Chella. Thank you.
So good morning, everyone. My talk will be about problem-solving learning, problem-solving skill from demonstration. And this talk is a part, is related to an European project, Humanoids, humanoids that learn socio-communicative skills by observation, in which my university, the University of Palermo, is a partner. The prime contractor is the University of Reykjavik. There are other people and also in this audience. So this is a brief summary of my presentation. I will talk about what does it mean for sensory motor skill models, and what does it mean to learn models from the low-level models and high-level model. And I will talk briefly about the problem-solving skills, and I will present the implementation of our architecture in the case of the well-known game Sokoban. Sokoban is a very well-known game. There is also a long history between Sokoban and AGI. There have been many papers also by Eric Baum, and also, if I remember well, also Ben Gozer wrote something about Sokoban. Anyway, Sokoban is a nice game. So the basic block of our architecture are the sensory motor skill. And we distinguish between forward and inverse models of sensory motor skills, while the forward model is a model where starting from the state and from the action, it generates the next state, while the inverse model is a model that starting from the action, the current state and the final state, it generates the possible action. So these models are very simple models of sensory motor skills. The main goal of our architecture is that this skill should be learned by the architecture. So what does we mean when we say when we talk about the learning skill model? There is the environment, there is some attentional control, and we extract pattern from the environment by means of the perception proposer, and we extract the more relevant patterns from the external environment, and we try to generalize in terms. There is a sort of there is a module that tries to generalize this pattern in order to extract the more general patterns related with the current environment. In the previous session, we were talking about compression of information. This is a kind of compression of information. So the system tries to extract meaningful pattern from the external environment and to generalize this kind of pattern. The master plan that you can see in the lower part of this picture, the master plan is the sort is the knowledge honed by the system. So it means that the master plan at the beginning starts with a very simple a priori defined skill model, both forward and inverse, and it contains some kind of innate goal and innate fact, and also a very simple ontology describing the relationship between entities in the world. But for this system to be successful, it is necessary that this master plan should be very, very poor, very, very simple. It should be some sort of epigenetic knowledge, as we can say, that the system holds. And the rest is the rest should be acquired by the interaction between the system and the environment. This architecture is very general. This kind of architecture is very general, and we tried to apply. We applied it in the Sokoban framework. I don't know if all of you know the Sokoban, and it's a very simple but very very simple game in which there is the actor, the player should push the block in order to put the block in their own position. So, for example, this agent should push this block to put it over there, or to put it over there, the agent cannot pull the block, and so a block can be blocked. So the agent cannot push, for example, two blocks altogether. If a block is so, for example, the agent cannot push this block in this direction because there is the border, and the agent cannot push two blocks. It is a very simple game, but it's very engaging. So I spent many hours of my flight from Palermo to San Francisco playing this soccer. So we want the system learn this kind of skills. And we had two different kind of learning. The low-level skill learning, which is based on essentially on motor bubbling, or what we call motor bubbling, in which the system tries to interact with the environment in a random way, essentially. So just like the baby-born child that tries to move their arms in a random way. So this is an example of, let's hope that everything is okay. Okay, this is an example of motor bubbling. The system tries very different strategies by chance, essentially, randomly, and try to extract the patterns and to generalize this kind of patterns. While the high-level skills is based on imitation learning, we can say, or learning by demonstration, what it says that it is more correct to say today. High-level skills are encoded by chains of very simple skills, and they are learned by observing actors, so by observing people playing this kind of Sokoban. In our case, we constrained all our PhD students to play Sokoban, and we have a long log of their game. In this case, there are 6 male and 3 female, and each learner played 12 trial on average, and we stored all their games, and we used this log in order to make the system learn the high-level skills. After this phase of learning, the system is able to use this knowledge acquired by essentially by simulations. In effect, the system is able to solve problems by using these skills, trying them in simulation. So the system has acquired in the master plan a long list of very simple skills. And in the situation at hand, the system is able to find the most relevant skill by simulating it in a simulation environment, and by deciding which kind of skill is useful at the moment. This is essentially the main idea of these systems. As I said before, the main block is the anticipation of the simulation manager. So the system is does some kind of planning, but the difference in the system with respect to the more classic AI planning is that all these skills are learned, and the combination of skills are learned by interaction between the system and the environment. So this is the main difference between our system and the more general systems. So let's see Okay, this is a very simple game played by soccer. You may notice that the system moved this block. Yeah, I'm out of time. So the system we can see again in the last minute I say. Okay. The system is realized that it's not possible to move the yellow block because it is blocked by the red block, and then before trying to block this one, move the block on the right. So it is a very simple form of anticipation in the sense that the system realized that it's not possible to move one block because it is blocked by another block in some sense. We evaluate the system by using the same people. We use essentially our PhD students, and it is a very simple system evaluation, of course, but it is an initial step in which we ask them how they consider the game played by the systems, and it was usually good or very good, especially when the system was able to perform some kind of anticipation. So this is important in my opinion, because it seems that the kind of the anticipation is a very main point for intelligence. And in the next step, we would like to continue in this kind of research, essentially by making the master plan the more simple the possible. So the system should be able to learn everything from scratch, and by interacting with the environment. Okay, thank you very much.
Our next speaker will be Alessandro Oltramari. I think it's this one, is it? Yeah. Okay. I will give you a sign and sit over there.
Yeah, sure. Okay, thank you. So in this talk, I want to present our paper concerning the extension of cognitive architectures ACTAR with ontologies in the context of visual intelligence system. As this work is a joint work with Kristinn Lebiere. So the problem enabling visual intelligence. So basically, we are working inside this Mind's Eye program. The Mind's Eye program is to develop in machines visual intelligence, where visual intelligence has to be conceived as the capability to learn generally applicable and generative representations of action between objects in a scene directly from visual inputs, and then reason over those learned representations. With respect to state-of-the-art machine vision, visual intelligence wants to do something more. I mean, when you deal with visual intelligence in the context of this program, the Mind's Eye program, we are trying to go beyond let's say, the state-of-the-art of object recognition and feature recognition, but try to understand which are the semantic, which is the semantics behind the actions detected, not just combining the objects, but try to understand the relations between those objects, so the cognitive relation between those objects. In this sense, we are not just trying to focus on the nouns that we recognize from the objects in the scene, but try to understand the verbs which we use to describe in a narrative way the overall action. This means that we are not just summing what we are seeing in the single sequence of scenes, but we are trying to understand something more, so the kind of underlying conceptual structure. In this sense, for example, if we look at this scene, this could be described like entering into the car, getting in, or this is like driving or leaving the scene. But then if you consider the overall input, if you consider a larger context like this, of course, getting in, driving, leaving the scene cannot be so together don't add up to a story. So the context here is very important. It's very important to understand which are the relations between all the objects and the different directions of the movement, for example, in this case, and the conceptual structure behind it. So, of course, this is a problem. This is a complex problem, and we are trying to get to propose a solution at eye level. Okay, so trying to combine both cognitive mechanisms and semantic context, which is let's say the framework of this extension of the cognitive architecture ACTAR with ontologies. What does it mean combining mechanism plus content? So if you consider human visual intelligence as where background knowledge makes the difference when dealing with complex cognitive tasks, like, for example, action recognition and disambiguation, as in the video that we have seen, in order to get this human-level visual intelligence for artificial system, we think that integrated knowledge systems need to be developed. And these systems focus on mechanism of human cognition, like, for example, control, learning, memory, perception. And in this sense, we are using ACTAR as the architecture focusing on the mechanisms. And concerning content, you need kind of knowledge resources, knowledge representations, like, for example, ontologies. In this sense, you can think of ontologies not only in terms of computational ontologies like OpenPsych, Dolce, Sumo, and so on, but also like computational lexicons, which are very popular, like WordNet and FrameNet and so on. In particular, so in the framework of combining mechanisms, cognitive mechanisms, with semantic context, we focus on the ACTAR mechanism and the so-called Homine ontology, which stands for hybrid ontology for the Mind's Eye program. In this sense, the integration between these two, let's say, knowledge systems, a different level of knowledge, of course, this integration helps to pinpoint the main roles played by agents and objects in actions, so in the scenes. For example, disambiguating the lexical meanings of the verbs and the nouns for detected actions. Recognize the cognitive patterns of action via their temporal and conceptual components. For example, so with cognitive pattern, we mean like something like the sequence, I don't know, walking, bending over, lower the arm, picking up an object, and bending, and so on and so forth. So sequences like that compose, for example, the pattern pickup or lift. So in order to have an instance of a pickup event, you need a sequence, both temporal and conceptual, of specific temporal specific components. Okay. And so in order to understand if a specific video, like the one that we have seen, evokes or not a specific pattern, we need to look for the components that compose that pattern. And in order to look for those components, for example, we can use mechanisms that are embedded in ACTAR cognitive architecture, like the base level activation, weighting the relevancy of components, some kind of partial matching, like providing similarity measures between components. For example, if you so there can be, from the semantic viewpoint, some verbs are similar and some other are very different. So the fact that if you see something like lifting, so if the system recognizes something like lifting is similar to pick up, or put down is completely different from pick up, and so on and so forth. Screening of activation, so assessing the specificity of components in context. This means that if you consider patterns of actions like pick up, bury, holding, or put down, what else, chasing, and so on, some of these embed movements by the agents which are common, which are shared. Okay, like walking is a movement which is very common and can occur in different patterns. And speeding of activations means that when you have a detection of a specific component, this component can activate different patterns, and depending on the importance of the component for the specific context, it will be activated a pattern more than another. And from the viewpoint of the, let's say, knowledge representation, this integration helps to reason over the logical constraints underlying actions. For example, we are using here an ontology, so homine ontology has been implemented in OWL 2, so having kind of, that is a kind of description logics. So zooming in, you can think about the input. So we have a kind of low-level processing, so visual classifiers that give us as input kind of object detections and so-called micro actions, which are these small components of general actions. Like for example, we get input like person steps forward from T1 to T2, person bends over from T2 from T3, and so on and so forth. And the output, the recognition of the action would be like person picks up hammer, okay, from T4 to T6. So the cognitive part, the disactivation of patterns, try to combine together the different input and to reason over kind of high level and more abstract verb for describing the action. And basically what we are doing is, so this processing of the input occur using ACTAR. So like for example, the base level activation is based on frequency data from the American National Corpus. This means that all these specific verbs that describe micro actions have an activation in the ACTAR cognitive architecture, which is based on the frequency of these verbs in a corpus. The partial matching based on similarity between components. And again, this similarity is between verbs and nouns, and similarity is based in this sense from gross vector measures. And speeding of activation, I already said something about that. Homine is based on FrameNet, a foundational ontology which is Dolce, which stands for Descriptive Ontology for Linguistic Cognitive Engineering, and some temporal reasoning. This is the example, an example that you can focus on. So you have like a P1, person 1 enter the scene, person 1 is in the truck exit left, and the person 2 run left. That is the description of the video we saw before. So together, these different micro actions can activate the cognitive pattern of leaving in the case of person 1 enter and person 1 exit in the car, and chasing when person 2 enter the scene and run left, which is the same direction in which person 1 in the car is leaving. This is a kind of description, a graphical description of the time course of activation process. So you see that after the first micro action, so after the first component, there is a good activation of enter, okay, so P1 enter the scene. Then when P1 is in the truck, you have kind of activation of other patterns. And at the end of the 4 micro actions, the fourth micro action, you see chase as the general macro verb activated. Concerning the ontological knowledge, just to mention that you can reason. So if the person is enter into the scene and then the truck exit left and the person is close to the truck, you can reason over some kind of a characteristic like this, that P1 pull the door precedes P1 is in the truck. Even though you don't have any input concerning the pulling of the door, you can reason about that, and you can infer that kind of knowledge. So future work, we are working on improving the interaction with the visual classifiers in order to provide top-down input to refine processing. We are trying to work on improving automatic inferences of relevant features of the action structures. And of course, we are trying to expand the kind of actions that we are able to recognize right now with this integrated knowledge system for augmenting the power of the recognition in the complex activities. Okay, thank you. These are the references.
Next, let's welcome Mr. Unmesh Kurup. I hope this one is the correct one. Thanks.
Okay. Thanks. Hi, everyone. So I'm going to be talking about some work we have been doing with integrating sort of state-of-the-art perception with cognitive architectures. This is work done with Kristinn Lebiere and Stentz at CMU. All right, so how can cognitive architectures support perception? And I'm coming from a high-level cognitive perspective. And generally what you find is cognitive architectures are good at one of two things. Usually high-level cognition, as the name suggests. In some cases, like EPIC, it's tuned towards perception. But usually one or the other, they just assume facilities are available and then work with what are called the products of perception. So what we are looking at is how can architectures such as ACTAR actually help improve perception. And there are at least three ways that we're looking at. One is obviously attention. Where do we look next? What do I look at? What is the context, right? So this is a street scene, and we know that there are going to be people on the sidewalks, there are going to be cars on the road, and we can use this information to actually make perception better. In fact, you can see that this is the output of a state-of-the-art person detection on the scene, and it detects a couple of people, it detects a couple of things that are not people, and misses one or two people. And information about context, like people don't usually float in the air, can help cut down on these false positives. And then finally, we refine the output in various ways. So what I'm going to be talking about in this talk is the refinement process using ACTAR. So here's a simple example. We call it the checkpoint scenario. Essentially, it's a checkpoint. A, B, and C are three vehicles waiting at a checkpoint. The checkpoint itself is not shown. And people, when they wait at the checkpoint, they get bored. They get out of the car. They stand around. They walk towards other cars, probably to talk to people. And then they walk back to their car, or they keep walking. The goal is to make predictions about what people are going to do and eventually when they're going to do it, and detect anomalous actions. In this particular scenario, there's only a single anomalous action, which is fleeing. You can guess where our money comes from. People get out of the car and just keep walking, and they don't look back or turn around or whatever. So what is the input to our high-level cognitive model? It is some ID vector. Right now, we're using, at least for this paper, it's just an ID. But we have also started using color and height, and eventually even pose, depending on how fast we want our system to run. There's also location information coming in, just an XY coordinate where this particular ID is to be found in this scene. And both of these things have errors associated with them. There are location errors. Some delta error is there always. And there is a 1 in 10 chance that the ID that is given is not the right ID for the object. So what the model does is that given this information coming from perception about an ID and an XY, it uses that to retrieve from its memory what's called an object information chunk. Again, a chunk in the ACTAR sense is just a frame which contains slot value pairs. And in this case, this particular case, the frame has the ID information, XY, delta values on how X and Y are changing, and an action slot. So it uses that information to retrieve this object chunk, and then updates this chunk with the new information it has about the new XY locations for this object. An action is always based on the rate of change of XY for the scenario. So if somebody is standing, the rate of change is very low. If they're walking, it's fast, and they're kind of standing around, it varies a little. So and then the key part of the model is how this information is retrieved from memory. And there are two parts of ACTAR that I'm going to be focusing on, which is partial matching and blending. And I'll get to both of them in a moment. I just want to say that in general, in ACTAR, when you retrieve something from memory, you specify certain constraints. You say, I want a chunk of this type, and all I know are the ID value and, let's say, the X and the Y value. And Actar will go through all its chunks, see which ones match exactly, and from those that match exactly, it picks the one with the highest activation value. And how the activation value is calculated, etc., is in the paper and in Actar literature. But what happens when you include partial matching and blending? What partial matching does is it retrieves chunks. It does not just retrieve chunks that match exactly. It retrieves chunks that match to the greatest degree. So there is a similarity calculation that happens that we can specify, and it calculates that and not retrieves chunks that are similar, not just those that exactly match. And what blending does is, given those chunks that have been retrieved, instead of picking one that has the highest activation, it generalizes them, essentially a weighted averaging depending on the last time, the activation values and things like that. So here's an example. I request a chunk from memory because I have from perception information that this object A is at 10, 10. And you can see memory has about 6 chunks. 3 of the chunks are about B. B is at 9, 10, 10, 10, 11, 10, and then A is at 100, 100, 102, 200, and 104, 400. What partial matching does is it looks at what I asked for, which is an object with the ID A, and says, look, I know you asked for A, but my similarity calculations tell me that the chunks for B actually match this better than it matches A, just because the values of X and Y are very different. And blending blends all of that information, those 3 chunks, into B 10.34, 10. And the reason why it is 10.34 and not 10 exactly is because it's weighted averaging in certain chunks have higher weights. All right. And so that's how kind of it deals with errors in identification. So for example, if you say it's this object A at 10, 10, it says, well, we think it's object B actually. There are also a set of actions. There are perceived actions which are straightforward. Somebody's in the car, they're standing around the car, they're walking. You can be more specific and say they're standing around this particular car, they're walking from car A to car B. And you can aggregate these actions into sequences and say this person started out by being in the car, and they got out, they walked to this particular car and came back. And that can actually be used to predict sequences of actions for other people. Again, the anomalies are the fleeing behavior. So here are a couple of graphs that show the results. In the top graph shows the actual path and the predicted path for objects. So the blue line is the actual path coming from perception, and the red line is the predicted path for an object. And you can see they match fairly close. By predicted path, what I mean is when an object information comes in, you can use the delta X and Y to actually predict where the object is going to be next. And that is what is retrieved from memory when you ask for a particular chunk. And the bottom graph actually shows the percentage correct of predicted actions at each step. And you can see this is simply the output of blending, and the drop-offs you see are when actions change from somebody's in the car and they start walking. This is better than a simpler prediction based on, hey, what the person is going to continue doing what they did earlier on. The problem with that is the delta X and Y values change a lot. They fluctuate, and it's hard to predict. So unfortunately, I don't have the graph of that, but they go up and down a lot. And what blending does is it smoothes over all of that and gives a slightly better result. So that's what we have done so far, and part of the work that we are doing now is using real-world data. So the data we were using were from simulations. We are working on real-world data, like the example I showed you in the first slide. We are working on adding context to our systems. So actually having the cognitive architecture suggest perception where to look for objects. The 2 pictures in the middle, they're not from our work, but from one of our collaborators. But you can see that the system is actually predicting these are where people are going to be found, and it predicts both. It uses both the geometry of the scene as well as information about the height of people in the scene. And one of the other things we are doing is actually predict, because we know where people are going to be, we are predicting that as well and suggesting to perception, hey, this is where this object is going to be next. And that's it. So there are some references, and this money comes from the Robotics CTA. Thanks.
This is why I use a Mac. Okay, next up is Benjamin Johnston.
Okay, I'm from the University of Technology, Sydney, and this is really an ideas paper about how you might collect and use large-scale databases of physical knowledge. My research interest is really in creating practical artificial intelligence, and specifically practical artificial common sense. And I'm trying to build artificial intelligence, so I'm not necessarily constrained by biological plausibility or human-like intelligence. As I see it, my philosophy is that the human brain and computers have very, very different machinery, so there's no reason to expect that a computer-based intelligence should operate in any way like a human intelligence. And I've been working from the assumption that we understand computers pretty well, and the question for us is really, well, how do we put together what we already know about computers in such a way that intelligence emerges? And so this kind of picture is a sort of inspiration that I'm working from. How is it that we as people can understand this image? I mean, it's clearly a chair, but it's also, you could say it's a hand. And so it's like a fusion of these two concepts, but it isn't a prototypical chair, and it isn't a prototypical hand. It doesn't really fit neatly into any particular concept. So traditional methods of AI don't really work well with this. Here's another example. The Chinese word for minivan happens to be bread loaf vehicle. And as humans, we can sort of see where this comes from. It looks like a bread loaf. And we can sort of see how this term might have developed in the Chinese language. But how is it we understand this? I mean, bread loaf vehicle and minivan are very different concepts. And if we think about a bread loaf, its defining characteristic isn't its shape. I mean, a bread loaf is really, it's something that's made of bread, and it serves more than one person. The shape isn't a crucial part of it. So my question then is, well, how do we deal with this world where words like chair and hand have vague meanings? Or how do we deal with concepts when they're used in ways that seem to violate their fundamental, their defining principles? And so, as I said, my research is about practical artificial intelligence. And so what's a practical solution to this? Well, I look at the techniques used in computer science and see that data-driven intelligence, data-driven AI is proving to be quite a powerful solution to some of these challenges of vague and uncertain data. It seems that if you have enough data and a fairly simple algorithm, you can get some pretty impressive results. So while IBM and Watson made some stupid mistakes, it also from time to time displayed sparks of intelligence. Bing and that other popular web search engine from time to time show quite uncanny levels of intelligence in answering difficult questions. And then ConceptNet is a fairly powerful common sense reasoning system built from large numbers of volunteer contributions. And it does useful reasoning, and it's also being used to bootstrap more deep and intelligent forms of, deep and more powerful forms of common sense reasoning. So perhaps data-driven AI can help us in this physical reasoning problem. And while the purists in the room might argue, well, this is not really the way we should be going, I think it's a very practical solution to the problem of doing very useful, deeper, useful reasoning in the real world, and it can help bootstrap towards more powerful forms of artificial intelligence. Okay, so then how would we, given that we're going to use given that we're going to try and follow a data-driven approach to physical reasoning, what representations would we use and how would we collect this data? In previous AGI conferences, I've presented an architecture that combines logical reasoning with physical simulation. And of course, I'd like to continue using those rich physical simulations I've shown here before. But I must pragmatically admit that they're a bit too complicated for this task at hand. They're too rich, and we really need something simple, something as simple as possible in order to be able to pragmatically build these large knowledge bases of physical common sense. So what do we want? We want a representation that's simple to store and analyze. It needs to be very computable if we're going to be dealing with large databases. It needs to be simple for people to understand, simple so that people can contribute these models, and also so that we as developers can embed them into our AGI systems and exploit it as much as possible. It should work with existing AGI systems and existing game engines, and it should be useful. I mean, we're doing this for a reason. It's not just a theoretical exercise. So what I think really fits this bill is voxel-based representations. Imagine if we had a huge database of Lego objects in the real world built out of Lego. So if the system wanted to know what a house or a car is like, it can just retrieve one of its many millions of objects. We've got motorcycle here. And these are simple representations, but they capture some of the essential properties of these objects. And this really comes to the point of this project, this paper, sorry. I've built an online tool so that to invite the public to contribute models that might be used in artificial general intelligence. So it's basically a 3D voxel editor. And we've got on the right-hand side here a 3D viewer. And the left-hand side, we've got a 2D editing surface. So I can start by building a model of a chair here. Ooh. This mouse is not working very well. So you can see I've created the base here, and then we can work our way up through layers. So it kind of works like a 3D printer if you want to view it that way. So we just build up the layers, build another layer. Let's give it a seat. I'll ignore that mess. A backrest. And so it only takes a minute or two to just add another model to this database of physical objects. And on the way, we can annotate it with knowledge, so we can connect it up to textual representations. So we can say that this part of the object's a backrest. And then we see in the notes being added there, and we can see our 3D object as we've created it. So in my experience, this is a kind of fun and useful interface. It's a quick way of collecting large amounts of data that could be useful. And it's related to some of the, it can be used in other systems like Ben Goertzel presented a voxel-based representation, a voxel-based 3D environment earlier. And this could be plugged into it. It's kind of related to Minecraft. And so far, I've got a number of submissions. They've all seemed to be quite creative. There hasn't been much yet. But then I imagine, well, what could we do if we had millions and millions of these 3D objects in the system? And I'll just do a simple example, referring back to this bread loaf vehicle. So, faced with this question of how to interpret what's a bread loaf vehicle, the system might pull up its model of a bread loaf, and it might pull up all the models of vehicles it knows. And it can just work through them and compare how similar they are. So we see that the minivan, the red minivan, happens to have the smallest error, 143. So we'd say, using this similarity measure, the minivan is most similar to a loaf of bread. It could also be used in other ways. For example, we could pull up all of our bread loaves, all of our minivans, and then ask, well, in what way are they similar? And so a color-based similarity, it's not very similar, but a size, comparing the size, there's very little similarity. But then if we do a scaled invariant shape comparison, like I've done here, we see that they happen to be very similar. And so this can help make sense of these physical reasoning problems. So this is really a sort of small and quick example of what's possible, and it's kind of a vision of what might come. We won't really know what we can achieve out of this until we've collected a large database and started putting it into more serious and big problems. But I hope that gives you an idea of some of the possibility. So you're welcome to contribute if you'd like to. Just go to www.commirit.com/objects and feel free to add a few models to help contribute to artificial general intelligence. Everyone has to tick off to say that they will release their work to the public domain, so I'll be able to share this work to everyone when it's complete. So thank you.
I would like to invite our speakers of this session for the panel. And if you have questions, I would like to ask you to line up again, because I think this method has worked very well. We can give you microphones then, and everybody in the room can hear your question. Please come to the front.
I guess this question is for the guys with ACT-R. I have read a little bit of literature by a fellow named Jeff Zox at Washington University on what he calls event segmentation. And I just wondered if you guys were aware of that, or if you do something similar. It's basically something like humans watch a video and they're asked to segment the video into events. And his basic thesis is that when a perceptual prediction fails, it signals an event boundary, and you need a new event or a new model to predict.
I am not aware of that work, but that is exactly what we are doing. So we have these predictions of what action somebody is going to do, and when they deviate, that's when we know that something has changed. And so that's when one action ends and another begins.
So when you detect a failure, is there a special, I guess, switch or something that, because in his model there's sort of like a gate where the model is sort of protected from change until there's a violation in its predictions, and at which point a gate opens and allows a new model to be formed?
No, but I think that's partly because of ACT-R's memory.
Mm-hmm.
So multiple models can exist, and whatever is highly activated is what is retrieved. At least that's my...
So something new is highly activated, and
yes,
and then that will come in. Okay.
Yeah, something new and something that has been retrieved many times is highly activated, and that's what we use.
Okay.
Yeah, concerning our model, we provide top-down kind of ontology-based sequence of those components for events recognition. So basically, these cognitive patterns are provided top-down and are used to, try to detect the overall sequence in the event. And as Unmesh said, then we use other mechanisms in order to.
If you were doing it in a very high-dimensional input like a video, how would you represent a model of a person? Or how might you do that?
What do you mean with the model of a person?
Um,
Like all the movements, actions, and something like that?
yeah, I mean, how do you project what that person will be doing in the next few seconds
Yeah, well...
in terms of a representation?
Okay. Well, basically, to make this projection and prediction, we exploit these patterns. So suppose that you see a person moving, like walking, okay, and then maybe extending the arm. The model look for, in the declarative memory, look for a pattern which is constituted by those two elements, and try to understand which are the next components in the various patterns, and try to do it like using spreading of activation and something like that. So it's not really a prediction, but it's a kind of comparison between the available patterns which have been provided by the ontology top down.
Okay, thank you.
Thank you.
So I had a question about the Sokoban. So you made an assumption that you have a very good simulation of the game, and then you can bootstrap anticipation from utilizing that simulation. I had a question about maybe an extension. Could you also, in parallel, learn the simulation model while learning the anticipatory moves? So maybe through body babbling or something along those lines?
Yes. Yes, the system is able to learn by analyzing other player. The simulation is used when the system have to choose which kind of action do in order to solve the Sokoban problem. So the system try to simulate which kind of action and try to individuate the action. There is a sort of heuristics that is inside that I call the master plan in order to evaluate these. In the current implementation, these heuristics is given by the designer, but we want in the next years want that this kind of heuristic should be learned by the systems.
And that leads to a follow-up question. And you mentioned that for future work, you might look at like you have a scene, you make an ansatz of where people might be, but you're not going to do, would you do feature extraction of where the sidewalks are independently, and then you'd say, okay, it seems like that's a feedback. You'd say, okay, I think these are sidewalks, but if they were, then there would be people on them, and I think those are people because those. So maybe you can talk to a little bit about how that would work.
Yeah, actually, part of that is so one of the people we collaborate with works in robot vision, and so they have these systems that actually do. They have an idea of the surface geometry, but then they use evidence from where people have been detected to actually improve that, and then so there is a feedback loop that they use. Unfortunately, I am not familiar with the math, but I can give you like references.
But so for both of your work, it's binary. You say yes, there's there's a person there with probability 1, or it's not even probabilistic.
Oh, the output of perception is a confidence value.
Okay.
Yeah. Okay. Yeah, and that we use that to bias our decisions.
Okay. Thanks.
Hi, Dr. Alessandro. Very interesting your talk. I have the 2 questions. One question is, what is real meaning is hybrid ontology? What is a hybrid? Is a real meaning?
Yeah, I'm using hybrid in the sense that we are combining different resources, both from the viewpoint of ontologies, so in the sense of formal ontologies, like we are expanding this Dolce ontology with some kind of domain ontology for our domain, but we are also extending this computational ontology using WordNet and FrameNet. So in this sense, I'm using hybrid. It's just that we are combining different semantic resources.
Yeah.
And so this is the.
So you all follow the WordNet or use the standard OWL like this?
Yeah.
What is your mainstream in your hybrid ontology?
Okay, so basically this hominy ontology is constituted by a top layer, which is Dolce ontology, implemented in OWL, in ontology web language. And we expand the top level ontology with WordNet and FrameNet, of course, translated into OWL. Okay. So basically, the ontology is formalized in OWL, but is composed by both, let's say, general formal distinctions like object, event, quality, agent, and so on, and populated with lexical meanings with WordNet and conceptual frames from FrameNet. Everything in a hybrid resource, let's say.
Okay. Okay. Second question is, I also look at heard your talk. Is you also use a formal logic to describe the hybrid ontology. What kind of logic you use it for this purpose?
Well, as I said, we are using the ontology web language, which is description logics.
Yeah, because
OWL,
it has a formal description.
Yeah.
What kind of the tools describe your hybrid ontology?
Yeah, I said the hybrid ontology is encoded in the ontology web language, which is description logics. So the expressivity of the language is description logics. Okay.
Okay. Thank you very much.
Thank you.
Hello. I have a question to the last talk, actually two technical questions. One is whether you provide the editor and the viewer as open source, and the other is related, is whether you considered plugging a depth camera or something like Kinect to it, and getting the point clouds, which are like voxels, and then just clustering it to decrease the resolution and getting the models just from rotating a camera around something.
Well, to answer your first question, the editor is, well, it's all JavaScript, so you can look at it, the source yourself. It's not great code, but the point isn't really the editor, it's the models that it creates, and all the models are going to be public domain. You have to tick a box saying releases to the public domain. As for collecting point clouds, that's certainly one thing I was considering. Well, you could have your robot explore the world and autonomously collect models, or even just give it models in a controlled environment, and that's tempting, but it limits you to the kind of things that you can show. So you couldn't show it you couldn't model a house or a skyscraper. It also means that the advantage of this is that it's just simple, so we can just create many models and then add textual tags onto it. So it's trying to find a compromise between rich detail and something that's simple and easily manipulated. So I'm going for the simplicity.
So what I meant is whether you could combine, like take a model from outside and then still edit it. And
that's certainly a possibility, yeah.
Sorry, I just realized that you're also implicitly capturing our intuitions about objects. You know, we feel these are the important parts of the object, which is something you would not get from just getting the point cloud.
And by using different colors, you're basically providing a segmentation to it as well. Yeah.
Did you consider plugging your designer into something like Minecraft?
I have considered it, but I haven't explored that at all.
Okay, so I think you have a big difference between the two architecture sessions in some way, because the first architecture session was more about how people wanted to do that. This is what kind of architecture they propose. Here it's more like what people want to do with it. That is, they present their work starting from tasks. And my question would be, do you think it would be worthwhile to open up the task sets to a more general audience? For instance, make the data public, make the task itself public, turn it into challenge problems. So, for instance, different approaches can compete with different architectures in order to identify people in street scenery or to play Sokoban.
Okay. Yes, definitely should be a good point. And in my opinion, all these tentative to have some sort of benchmark in the story of artificial intelligence has not grown so much actually, because typically you first start with the architecture and then you try the tests that suit well with your architecture. However, I can say that one point should be to try to have some sort of instead of putting the tests and says my architecture performs so and so, your architecture performs so and so. My impression is that what is missing in AGI, and not only in AGI, it is a sort of a more software engineering approach, according to which I might use your modules for my architectures, and you can reuse your software. So I remember that, for example, when in some years ago in RoboCup there was a standard architecture which was the dogs for zoning, and all the people developed software for that kind of robot architecture, and there was a fast growing kind of general knowledge. In my opinion, what is missing are not the tests, but this is a sort of a standard framework in which people can reuse software. But what is needed is a sort of more serious software engineering approach to AGI. This is my point.
Okay, but we do have a lot of engineering approaches. I know of about a dozen toolkits at least, and I only know a small minority which are open to the general public, where people can contribute, that are used by various groups and so on, and which people try to promote. So it might not be actually the lack of proposals, but the thing is that there is just no reason to use a particular toolkit if it doesn't help you to do a particular task better. So in RoboCup Simulation League, you have several frameworks which people tend to reuse, but it's only because it helps them to do the task better.
Yeah, that's true, of course. I don't know. Yes, I understand that there could be a lot of possible tasks, of course.
So I think in the short term, yes, but in the long term, the advantages to AGI of having competitions is unclear. I mean, and the part of it is only because of the difficulty in defining tasks. So for example, if you take, let's say, a benchmark as modeling a 3-year-old, the problem is that the most interesting thing about a 3-year-old is that in 10 years he'll be a teenager, right? It's not what they can do now. It's in 10 years they can do even more. And sort of capturing that as a test is hard. I mean, somebody has to work on it.
You should look at the YouTube video of Star Wars explained by a 3-year-old. I'm not sure if there's really a bigger progression after that. I think she can do it all.
Yeah, I think that one of the point of opening the data sets and also trying to evaluate the tasks is very important. And for example, in the context of this Mind's Eye program, where the data sets are not open, of course, because they're not funded, there are different teams that compete in trying to solve the general problem of the event recognition, right? And so we are evaluated with respect to those kind of standards for the event recognition. But the problem is not just, I mean, if you want to evaluate, and this is a general comment that I had also from last days, if you want to evaluate or try to compare different AGI systems, you need to be able also to map the different architectures in my view, and not just at the level of mechanism, as I try to point out in my talk, but also at the level of representation, because many people talked about universal mental representation, maybe you or neurocognitive representation, mental representation, but when you try to understand the semantics behind it, how do you do? So if you want to evaluate the real power of the representations, you need also some kind of mapping between the representation. So yeah, these are my comments on your question.
I think maybe some challenge problems can provide such mappings. We have seen this excellent example by Benjamin, which harnesses the power of the internet to make people collaborate on things like this. Now imagine you have something like a street people recognition task. You make a data set public, and it's one of many challenges which are available on a challenge website, and people can just get in there via a standard API, use whatever solution they have, and have the grounding via the data, because they have to fulfill the task, and you can have something like an automated competition.
Yeah, yes, I agree. But one word is, if, for example, sometimes ago I was involved in the NIST competition of recognition of data of print and data set of written data set. And at the end of the story, the winner strategy is to try to find a bag of tricks, an intelligent bag of tricks that is able to solve this very special kind of process. There are no artificial general intelligence. There are very intelligent bag of tricks completely focused toward the problem. So this is, in my opinion, the risk of having some kind of testbed. Maybe I don't want to.
I know people probably want to go for lunch, but so I'll be quick. But
we still got a few minutes.
Okay. I've been thinking quite a lot about requirements for simulated environments and also real environments to produce appropriate challenges for the goals that I'm interested in. And I know that they're not necessarily the same as everybody else's. I'm primarily trying to understand myself, and that includes understanding my evolutionary precursors, and that includes understanding some of the things that branched out from my evolutionary precursors. And I think that one of the features of the space in which I and myself, aged 1 and 2 and whatever, and other organisms inhabit, is that it is not much like the kinds of things that people tend to build into their AI test beds. For instance, Tile World, where you can only move in 4 or 8 directions. Or Lego, which is fine. I mean, young children do play with Lego and so on. But if you're interested in processes, well, with there becomes a question, are you going to include the process of constructing the Lego thing? If you do, then you're getting closer to the world in which animals live, where there are processes going on all the time. And in fact, one of the things that's wrong with almost all research in vision is that it assumes that the basic thing is to identify something static, an object or a relationship, whereas most of what we see and most of what most animals see are processes. And so if you want to put processes in, then that's going to change the data structure almost certainly, because I suspect there are things that are going on during the editing process which aren't there in the simulated world, like the block moving from here to there and all the intermediate positions which don't fit into a kind of grid-like structure. Anyway, last point about it is that if you want to look at processes, if you think of the processes in terms of how objects, as we think of, bounded, relatively rigid, identity-preserving things, change their relationships and their positions, that's much too narrow, because we need processes in which things are bending, processes in which things come into relationships where the parts of the objects are important. So the fact that it's your fingertips that are trying to grab the pin that you're picking up is important, rather than that your hand is trying to pick it up. And if you don't know that it's your fingertips, then you won't be able to debug things that go wrong. So I think we need to find what the underlying fragments are. Fragments of process and fragments of structure, and what the fragments of change are. And if we can build those into a nice toolkit, then of course we have the further problem of how they're going to be represented by a perceiver. And that's another bag of worms, as shown, and I'll just leave this as a thought, by how we see impossible objects, like the Penrose triangle and the Rotesvard triangle. They're clues that the human vision system does not produce 3D models of what's out there. It produces something much more sophisticated and abstract.
I very much agree with what you just said, but I'll just take it in a more narrow implied criticism that I'm collecting only static objects. My reaction to that in just the short term is really that I think that with enough physical models, you do start capturing some of these dynamics. So you could have a car, then a broken car, and a car that's smashed, and
a car that's started and a person in a car, and then you can see that the person's connected to the steering wheel and so on. So I think that's a small step towards this longer vision I certainly share with you.
Okay, we have time for a final question. But if you want to remark
just
something
a small
first.
comment, which was that there's not. It seems like there are even multiple representations and there's this disconnect between, for example, some of my some concepts are our idea of representations of objects are even platonic in a way, but at the same time when you're working in the real world trying to pick something up, that doesn't work anymore. And we seem to have both of these at the same time without conflict.
My response to this idea of creating benchmarks is, well, a lot of benchmarks do already exist, especially in the machine learning community for things like image segmentation. And I didn't look up the website I was thinking of before coming up here, but there are large collections of different problems and then rankings of different algorithms on these problems and that sort of thing. So my question is, what do you think is still missing from that sort of thing?
I think so. Essentially, what's missing is that the point about it's not about simulating a 3-year-old. The interesting fact is down the line they're going to be even better, and even for age closer to like symbolic data sets, there's like the lemonade game. There's the test that goes on, the prisoner's dilemma. There are competitions that go on for those things. But if you can define a problem well, you can create anything, you can create something to solve it, and at that point it's less interesting. It's the vague problems, the problems that have not been defined, solving that is the interesting part. So if I think of a new problem and tell you about that problem, you can solve it, and I think that's the interesting part, and this defining it seems hard.
Just a remark. We want the problem. One of the problems is that we want to capture things that are difficult to describe in terms of data sets. For example, creativity. Which kind of data set do you propose for trying creativity in a system, or something like this? So, in my opinion, AGI want to capture things that are not captured, that are not easy to describe in terms of pattern matching or data classification. So.
Last year, I had a paper on a benchmark problem that tries to capture what I thought was a deficiency in using data sets, and the problem was to give a robot a closed box of toys it doesn't know about, and it's got to spend time exploring and playing with those toys, and then after that, answer questions about those toys, like what would happen to this toy if I did this to it, or maybe it has to put the toys back into a toy box. And so that was my attempt to try and capture this need to have a controlled situation, like a benchmark as a benchmark, but also allow for uncertainty and this need to build new models of things. Like it's never seen an iPhone before, so it has to figure out how to play with it. It's never seen a rubber ball. It's only seen steel balls before, so it has to build a model of what's rubberness, and so on.
Yeah, can you imagine something like, imagine you have seen the bread box vehicle, you have seen the bread, you have seen the vehicle, you have seen a computer come up with an interpretation or rendition of a bread box computer. I know I had one back in the day, but... Okay, I do thank you very, very much for your contributions today. Thanks for the panel discussion. It was very interesting to me, and for the nice talks in the session. And have a good lunch, and see you after the lunch.